Hello, and welcome to the second session of the STEM.LD Leader Orientation Series. In this session, you will build on what you learned during Session 1, developing a vision for STEM at your school, and consider how you can support strong instruction in math and science to help you realize your vision. This session is designed to take approximately 90 minutes to complete. Over the course of the session, I'll prompt you to pause the video to engage with your resources through reflection and practice. I'll give you cues for approximately how much time to spend on each activity, though you should feel free to move at your own pace and slow down to take as much time as you need to complete the activity before you begin moving on. When you see this orange folder symbol, you'll want to open the STEM.LD resource folder and access a document from that folder. When you see the blue light bulb symbol, you'll want to pause the video for reflection. And when you see the green pencil symbol, you'll pause the video for some practice. At the very end of the session, there will be a short survey that will record your attendance and completion of the session. Resources for the session today can be found using the link in the deck or the QR code on your screen. In this session, we will spend time understanding how you can support strong instruction and what teachers are learning through the STEM.LD partnership. We will dive into how you can best leverage instructional walkthrough tools like the Tennessee IPG for Math or the TNTP Science Walkthrough Tool to identify areas of strength and development when observing instruction. Additionally, we will introduce the structures of support embedded in the STEM.LD grant and give you time to think about how you will position the teachers in your building to get the most out of these supports. Here's our agenda for today's session. In your previous session, you thought about your vision for STEM in your school. And this session, we'll start by talking through some key components of strong instruction in math and science, and move into thinking about what tools and structures might support that work. It will be particularly helpful for you to have your STEM vision nearby to ensure it aligns with the components of strong instruction in math and science classrooms. We will close out the session by giving an overview of the support structures that you can expect from the STEM.LD partnership this year. Take a moment to reflect independently for a few minutes on what is currently happening in math and science classrooms in your school. Consider what instruction looks like and how you think kids might feel about entering math and science classrooms. How do they feel about the work that they're doing, and what do you see happening currently in your buildings? Like many things in the education space, we know better now than we did when we were all in school. So what I'm going to share today may not be how you experienced early science teaching and learning. It might not be what you're currently seeing happen in your buildings. It certainly wasn't how I experienced science. But we are in a place now where we have a better perspective on what skills and dispositions are going to be necessary for our kids to be prepared for 21st century jobs. The jobs we are preparing them for are not the jobs of today and are certainly not the jobs of 20 to 30 years ago. So our preparation must shift and change as those careers shift and change. With the development of AI and other technological advancements, we are no longer in need of students memorizing or reciting scientific information or facts. While some basic skills and knowledge are critical in any subject area, in order for students to access higher level thinking and ideas, they no longer represent the end goals of instruction. We want to see science classrooms and science instruction shift from more of a focus on learning about science to figuring out science. This means that we want to see instruction that is centered on figuring out how a particular scientific phenomenon happens or solving novel problems using their scientific reasoning. Additionally, the instruction should be coherent for students. Like each day is adding on to a larger story that helps them more deeply understand a component of the science concepts. Finally, we want to see instruction that is driven by evidence, meaning students are gathering little bits of evidence in each class session that help them revise and refine their initial ideas of why something happens or how something works. Take a minute to read this definition of what we mean by phenomenon. Ultimately, we want to make sure that when students are in science classrooms, they are spending their time trying to make sense of the world around them. Phenomena don't need to be fancy, and they also don't need to be something that can happen within the four walls of a classroom. They just need to be something that can be experienced and observed, and that can be explained or predicted by scientific knowledge and ideas. Read through the 4 statements at the bottom of your screen. Pause the video to practice figuring out which statement represents a phenomenon. If you said statement 3, you are correct. This is an observable event that is explainable using science concepts. Option 1 is an example of a science concept or principle, and while this is illustrated by the phenomenon explained in number 3, it is not itself a phenomenon. Number 2 is an example of a question a teacher might use to introduce a science concept. While guiding questions are a good instructional strategy, they do not indicate that instruction is grounded in phenomenon. And finally, number 4 is a question guided by an observable event explained by using science concepts. It's not a phenomenon because we've already told kids the question. Ideally, we want them to make observations and come up with questions about the phenomenon on their own. In addition to grounding instruction and figuring out phenomenon, we want to make sure science instruction is coherent from the student's perspective. A storyline approach is often used in high-quality curriculum and planning to ensure that lessons are sequenced and developed in such a way that kids are able to follow the story of the learning. This graphic from Open Syed identifies some common practices and routines embedded in their lesson structure that support students in following along with the story of each unit. By having lessons flow together in the storyline format, we're supporting students in making sense of the world. This is the skill and way of thinking they are going to need to solve new and novel problems. Knowing word definitions or examples of concepts, even getting to do a lab that models a concept, these experiences are not experiences that actually build students' ability to solve new problems. When you're walking into a science classroom, these are some questions you might want to ask yourself. Take a minute to pause the video, read through and reflect on the questions identified on this slide. What's resonating with you? What is this stirring up for you? Now we're going to do a little bit of practice. We're going to pause the video and read each scenario. Consider the questions we just discussed that helped you determine if the lesson is grounded in sense-making. Which of these scenarios do you think allows for sense-making, and how do you know? Pause the video here to write down your reflections. In scenario 1, students are reflecting on their actions and considering how they can be better stewards of natural resources. While this may be a worthwhile task, it does not require students to engage in sense-making. In scenario 2, students are responsible for creating, changing, and analyzing based on real evidence they are collecting. They are trying to figure something out. Scenario 2 allows for more sense-making. Okay, we're going to do a little more practice that will hopefully help us get better at identifying strong instruction. This time we are going to focus on identifying lessons that are driven by a phenomenon. For this practice, you're going to need to locate materials in the session folder. There are 2 handouts in the materials folder labeled 1A, which is a 4th grade example, and 1B, which is a high school example. Just select one of these sets of assignments to read through, and while you're reading, consider which of these is a phenomenon-based assignment. Pause the video here while you read and analyze the assignments. In the 4th grade set of assignments, the one that is actually driven by a phenomenon is the first lesson, which shows a video of water moving and splashing in a petri dish. You'll notice that the lessons following that anchoring phenomenon focus on students observing, creating, building, and developing their own thinking related to figuring out what is going on with the water in the petri dish. In the plant's parts and their functions set of lessons, the sequence of lessons does not allow students to observe something in order to figure it out. There is more of a focus on recall, and the lessons are not woven together like a story that leads to a deeper understanding of the topic or phenomenon. Rather, they are discrete activities, all under the same umbrella topic. In the high school lesson example, you will notice the same thing in regards to the progression of lessons. In the dinosaur example, the progression is a set of discrete lessons that connect to the idea of evolution. In the ecosystem example, each lesson builds off of the one before it, deepening student understanding of the phenomenon and allowing them to develop models and share and develop thinking as they are learning and observing more each day. In summary, science is fundamentally about making sense of the natural world. Sense-making is the conceptual process in which a learner actively engages with the natural or designed world, wonders about it, and then develops tests and refines ideas. We often use the phrase figure something out. When you are trying to figure something out, you're trying to make sense of it. You're engaged in the process of sense-making. Essentially, sense-making is about actively trying to figure out the way the world works and exploring how to create or alter things to achieve design goals. The standards have shifted instruction away from simply knowing science to emphasizing using science and engineering practices to make sense of the world or solve problems. Instead of telling students, teaching them science ideas or facts, we should be engaging them in practices that allow them to figure out those ideas. Phenomenon-based learning means that students are engaged in working to figure out a phenomenon or design problem and learn science ideas through that process. That is a significant shift from how science has previously been taught, where the teacher gives knowledge to students through lecture, information, even labs that demonstrate scientific ideas. When you're observing in science classrooms, ask yourself, what are students working to figure out in today's lesson? TNTP has a tool that can be used to support you in giving feedback to teachers and to understand if you're seeing strong instruction as you observe classrooms. This tool can be found in your resource folder. We will practice utilizing this tool a little bit later in the session, but I wanted to note that phenomenon and sense-making are reflected in this observation tool. Additionally, this is the tool that we will utilize when we come to do instructional walks with you in your buildings through the STEM.LD grant. We are now going to shift to talking a little bit more about strong instruction in mathematics. Strong instruction in mathematics relies on the implementation of two sets of complementary standards. The standards for mathematical practice, which tell us how students should be learning or practicing mathematics, and the standards for mathematical content, which tell us what students should be learning and mastering in each grade level. The standards for mathematical practice are transferable ways of thinking that support students in developing critical thinking and strategic problem-solving skills. When they are integrated well, students are doing a lot of the same kind of figuring out that we discussed when we talked about strong science instruction. As we have come to learn more about the ways in which students learn mathematics, standards across the country, including those in Tennessee, have shifted to be more focused, coherent, and rigorous. Ideally, the way time and energy is spent in the math classroom allows students to focus deeply on the major work of each grade. The goal with focusing standards is to spend time deeply learning the most essential content rather than learning about many topics each year at only a surface level. The standards also connect content across grades so that students can build new understandings onto foundations built in previous years and link to major topics within grades. Underlying the coherence of the standards are learning progressions or vertical alignment, grounded in cognitive science and how people learn. Helping students and teachers understand the framework of building from relevant situations to conceptual understandings and representations and knowledge and skills. The aspects of rigor guide teachers to pursue a balance of conceptual understanding, procedural skill and fluency, and application, but not necessarily in that order. At some point during the adoption process for new textbooks and standards, you have likely heard about these shifts. The Tennessee Instructional Focus documents are a great resource to support your understanding of what strong instruction looks like at the standards level. The Instructional Focus documents, or IFDs, which can be found on Tennessee's Best for All Central, are a great complement to the IPG that leaders have used over the past year to support and give feedback to teachers. While the curriculums that districts chose were all vetted and determined to be aligned with the standards, there are different levels of rigor reflected in each lesson. The instructional focus documents can help teachers and leaders understand where they should be spending more or less time within their lessons, depending on the intent and rigor of a particular question, as it is aligned with the standard. This tool is particularly useful in planning, but can also be helpful while observing instruction to determine if the teacher is spending their time at the correct problems. Now we are going to do some practice related to strong instruction in math. You will need to pause the video to access documents in the session folder. The math lesson document has expanded versions of 2 different lessons related to the same standard. Pause the video here to read through these lessons and jot down what you notice about the different approach to teaching the same concept. Consider which lesson example would best position students to develop a deep conceptual understanding of solving one-step equations. In the SOC example from Illustrative Mathematics, students are constructing understanding, talking to peers, connecting new learning to new information or models they have already been exposed to, and sharing developing thinking. In the maze worksheet, students are simply practicing. While strategic practice is a great instructional strategy, it is often used in place of teaching the underlying concepts that help students apply their learning to new and novel situations. Similar to the TNTP science tool, the Tennessee Math IPG helps envision strong instruction in mathematics and gives leaders clear language to give feedback to teachers. Take a minute to pause and reflect. What do you notice about the IPG that aligns with the type of instruction and shifts in standards that we have discussed? In Core Action 1, you'll notice that the focus, coherence, and rigor at the center of instruction is the main thing that you're looking for. These shifts should be reflected in teacher practice. Additionally, Core Actions 2 and 3 require teachers to have students share their thinking and adjust their instructional strategies related to what students bring up through their thinking and sharing of ideas. Lessons that allow students to talk, collaborate, and share their developing thinking are going to better position teachers to know what students understand and be able to draw from that understanding and build on it to further deepen their understanding. Now, we're going to dive a little bit deeper into looking at these tools and practice observing instruction with these science and math observation tools. Take a moment to make sure that you have both of the instructional tools up on your screen, the Tennessee Math IPG and the TNTP Science Instructional Walkthrough tool. Take a moment to pause the video and consider what overlaps you see in the science and math tools. Where are there some differences in language or approach that we would expect to see in math and science, and where might there be some overlap? Hopefully you notice that there is a lot of overlap between these tools. Both tools have a section for culture of learning where we are looking at the classroom culture, the student agency, the identity that students are bringing into the work. Both require instruction to be aligned to the rigor of the standards and to reflect shifts in the standards, both 3D science practices and the science tool, and the focus, coherence, and rigor of 21st century math standards in the Math IPG. Both look at how teacher actions are driving instruction. Instructional strategies might differ by content area, but they both require teachers to display strong instructional strategies like utilizing a variety of explanations, models, and connections to prior learning, sharing right and wrong answers, and letting students reason through their ideas. Finally, both also want students to show ownership of the learning. This might look like productive struggle, students doing the majority of the work in the classroom, and really talking about modeling or drawing about their thinking. Now we're going to take some time to watch strong instruction in a math and science classroom. As you watch each video, try to record evidence of the action areas on the corresponding observation tool. Then identify 2 to 3 pieces of feedback you might give the teacher aligned with the IPG or the TNTP Science Observation Tool. As a reminder, this exercise is not intended to be used as a teacher evaluation, and we don't use these tools as teacher evaluation tools. Rather, we're using them to help give leaders and observers the language to give strong feedback on the shifts in instruction across science and math classrooms. If you choose to watch the math video, you'll see a teacher lead an exploration of dividing fractions with 6th grade students. In the science video, a class is exploring the movement of Mount Everest, which is the anchoring phenomenon for the rock cycling and plate tectonics unit in Open Sci-Ed. This video is also used in the curriculum launch Teacher Professional Learning to explore the first element of the anchoring phenomenon routine within the Open Sci-Ed materials. At this time, you should pause the recording to access the video links in our shared resource folder. Watch the video and identify 2 to 3 pieces of feedback you would give the teacher aligned with the Math IPG or the TNTP Science Observation Tool. How did you do? Do you have language in your feedback that aligns with the language in the Tennessee Math IPG or the TNTP Science Observation Tool? Are you being specific about what the teacher is doing well as it relates to those shifts in strong instruction? And are you being specific about the opportunities or areas for growth that the teacher might be able to leverage? Now we're going to move into talking about the STEM.LD support structures. These are the structures that are put in place to help you get better at giving this kind of feedback as you're walking and observing classrooms. This slide identifies the type of support structures that are in place through your participation in the STEM.LD grant. We'll talk through what each support is, who the audience is for these supports, and what you can do as a leader to support these structures. First, we offer teacher training. This is professional learning sessions for teachers to learn more about grade instruction in science and math. The audience for this is teachers, but what you can do as a leader is to ensure that substitutes are available for days when teachers need to miss school. Have teachers share what they learned back with you or others following the session to support the longevity and sustainability of their learning, and provide PD hours and mileage, whatever else teachers need to be able to make it to the trainings that we offer. As another support, the STEM.LD grant will provide professional learning communities for teachers. These sessions happen monthly, and they're 1-hour virtual sessions where we convene teachers from across the region to support continued learning with math and science. We have teachers share practices. Often we look at video from some of our walkthroughs and help teachers reflect on where they're making shifts and growing within their practice. As a leader, you can support teachers in getting to these PLCs by providing release time or PD hours for the ones that teachers attend, ensuring that they're free at the time of PLCs, meaning that they don't have bus duty or an after-school club scheduled at the time of these PLCs, and identify a point person that will support attendance and follow up when folks are absent. Finally, we'll offer instructional walks as part of the STEM.LD support structures. In an instructional walk, folks from our TNTP team will come on site to walk through science and math classrooms with leaders and support your feedback process. We'll use the tools that we practiced with today to help you give real feedback to teachers that aligns with a strong instruction. The audience for these instructional walks is both teachers and leaders. Teachers will receive feedback, ideally from you or someone in their building that is already maintaining a strong relationship with them, and you'll receive support in how to look at and observe science and math instruction in order to give the most high leverage feedback. To support this structure, you can ensure that you are available to attend walkthroughs and invite others on your school leadership team who you think might benefit from this learning. You can follow up with written or verbal feedback to teachers following the visit and make sure that teachers are prepared to accept visitors into their classrooms, that they know we're coming, they know what time we're coming, and that they're prepared to put their best foot forward. We'll now move into doing some final reflection and closing. Pause the video here and take a moment to reflect on your learning from today's session. Consider how can you support teachers' participation in the STEM.LD grant as a lever to realizing your vision for STEM within your school. Try to identify an action step that you can take following this session to get started. At this time, please take a minute to complete the attendance survey using the QR code or web address shown on the screen. Once you've completed the survey, you will receive a confirmation email with the name and length of the session. If you have additional questions or want to share some of your reflections from this session, please reach out to me at the email address shown here. We look forward to working with you and your teachers through the STEM.LD grant and getting to see your buildings in action. Thanks again for your participation today.